Next, we are going to look at what is simple harmonic motion and all the equations that we can use to represent simple harmonic motion. Now, simple harmonic motion is actually a type of oscillation, right? So we can say that a simple harmonic motion is definitely an oscillation, but not all oscillations are definitely simple harmonic motion. Because if they are simple harmonic motion, then they must obey this definition, in which a periodic motion in which the acceleration of the body is directly proportional to its displacement from a fixed point. So that's the first important part. In that acceleration, in that simple harmonic motion, the acceleration must be directly proportional to its displacement from a fixed point. That means the further away from the fixed point, the bigger the acceleration. And the second part, and the acceleration is always directed towards that point. Meaning to say, wherever the object is moving, the acceleration must point back to the fixed point. And the fixed point is also called the equilibrium position, or the one that is the middle. All right. Now, what are some of the terms that we use in simple harmonic motion? Some of the terms are pretty common, like period and amplitude and frequency. And some are not so common, like angular frequency, which I'll explain in a short while. So period is a standard meaning or definition, time taken for one complete oscillation. Amplitude is a maximum displacement from the equilibrium position, right? So I want you to add in the words from the equilibrium position. And frequency is number of oscillations per unit time. All right. Now we're going to come to a new term here called angular frequency. Now, what is angular frequency? Now, if let's say you have the frequency, let's say 5 hertz, it means that in 1 second you perform 5 complete oscillations. But you wanted to express that 5 oscillations in terms of radians. So you want to convert into radians. So what will you do? Now, recognizing that one complete oscillation is equivalent to one complete revolution, because when you complete one oscillation, you are actually starting from a point and coming back to the same point. So it's the same as starting from a point and going one round and coming back to the same point. So we can call it an equivalent. So which means to say one oscillation is equivalent to one revolution. In terms of radian, is 2 pi radians. So in other words, every oscillation is supposed to be equivalent to 2 pi radians. So if you have your frequency f and you multiply 2 pi, so that means every oscillation that you have in 1 second, you multiply by 2 pi, you get the equivalent number of radians that you complete per second, which is why it's defined as frequency expressed in radians per second. So you can use 2 pi f, or because we recognize that f equals to 1 over period, we can also get the formula omega equals to 2 pi over period. Okay, so now I'm going to show you an example of how to use a typical simple harmonic motion example to prove this definition, right? So let's look at the case of a mass spring system. And let's say, maybe let's say we start off with a spring with an which is not loaded yet, and we say the original length of the spring is L. And what we do then is we hang a small mass, so it will stretch a little bit. All right, so let's say the weight here is mg, and let's say now the extension of the spring is E. So therefore, the restoring force exerted by the spring on the mass will definitely be Ke, according to Hooke's law. Okay, so you have this Ke and mg. So for this part, we can say that Ke equals to mg because it is in equilibrium. So let's look at what happens now. If let's say we take the spring as before, let me just draw back the same place here. Alright, so let's say this is the new height here, new length here, sorry. And what we do now is we pull the mass a small distance downwards. So let's say we pull it down to here. Alright, and then it will oscillate up and down as well. And let's say it moves up and down by a small distance, x. So we are pulling it down by a small distance x. So now it will move up and down by a small distance x. So what will happen now is that we are going to consider the net force acting on the body when it's at the lowest point and also the highest point, right? And also in between also is the same lah. So let's look at the lowest point first. So what are the forces acting on the mass when it's in the lowest point? So obviously we will still have the weight, and then now the restoring force of the spring will be K. Now notice the extension now is E plus X. So the total extension is KE plus X. So therefore the restoring force is K E plus X. So now if we were to examine which force is bigger, we will notice that obviously KE plus X is bigger than mg, because the extension here is bigger than this extension. So therefore this restoring force here is much bigger than this, so this will be bigger than the weight. So the equation will be net force equals to K E plus X minus mg. Alright, and if we were to expand it, Ke plus Kx minus mg. And then you will notice that since your Ke is equals to mg, so this Ke minus mg will cancel off. So you'll be left with only Kx. And this Kx is your net force, which is equals to ma. So can you see now that the acceleration is directly proportional to the displacement? Your A is directly proportional to displacement. And which direction is your net force? Do you see that because your Ke plus X is bigger than mg, so your net force is pointing up. So if your net force points upwards, your acceleration also points upwards, which means to say your acceleration is directed towards the equilibrium position. Now then some students ask me, what about the if it is on top, will it be also the same equation? Alright, so let's look at this. When it's at the top here, which is here, what are the forces acting on the mass? You will still have your weight, and you will still have your restoring force of the spring, but notice that the extension now is less. You have a total extension of E minus X, because you had E, then you went up by X, so your balance is only E minus X. So therefore, the restoring force of the spring will be Ke minus X. So once again, if you look at the forces acting on the mass, you will notice that mg will be bigger than Ke minus X, because if your extension is E, you can balance the weight, but now your extension is less than E, so it will not be enough to balance your weight. So your weight will be bigger, so your net force will be equals to mg minus Ke minus X. And so what you will get is, if I open up the bracket, you get mg minus Ke plus Kx. So once again, remember we said that your Ke equals to mg. So this mg minus Ke will cancel off. So once again, you will get Kx. So this Kx is your net force, so it equals to ma. So can you see once again the acceleration is directly proportional to your displacement. And you notice that the net force is actually pointing down, because we said the weight is bigger than Ke minus X, so the acceleration is also pointing down. So that means the acceleration is also pointing back towards the equilibrium position. So we can safely say that this mass spring system is definitely a simple harmonic motion, because it obeys our two conditions. Acceleration is directly proportional to displacement, and the net force, or rather the acceleration, is pointing back to the equilibrium position. Alright, so this is how we know whether the oscillation is simple harmonic or not. And I also want to just add that this angular frequency, if you notice that we have seen this symbol and formulas before in circular motion, but in circular motion we don't call it angular frequency, we call it angular velocity. So why here we cannot call it angular velocity is because the definition of angular velocity is not suitable for this simple harmonic motion. The definition of angular velocity is angle turned through per unit time, and as you can see in, for example, the mass spring system here, so the mass is not actually moving in a circle, so there's no angle turned through. So to use the term angular velocity would be unsuitable, so which is why for oscillations we will use angular frequency, even though the formula and the symbols are similar to angular velocity in circular motion. So don't forget, for circular motion you use angular velocity, and for simple harmonic motion, you call it angular frequency. But the formula and the symbols are all the same. Now, in simple harmonic motion, which is a type of motion, we are still going to examine quantities such as displacement, velocity, and acceleration, which are all vector quantities. So we're going to look at how to determine whether the displacement, velocity, and acceleration are positive or negative, and when do you get maximum values for each of these quantity. So we're going to assume in this case a mass spring system again, okay, as it moves up and down, and we're going to take the upwards as positive as our sign convention, which is the usual sign convention. Now let's say the object is moving from the middle to the highest point. Now along the way, displacement will be considered as positive or negative. Now, remember what we've learned in kinematics in AS. Displacement only depends on which side of the equilibrium or which side of the reference point it is at. So it doesn't depend on direction of motion, it doesn't depend on whether it's going faster or slower, it just depends on where the object is at with respect to the reference point. So the reference point here is the equilibrium position, and you're taking upwards as positive. So if the object is anywhere above the equilibrium position, the displacement is definitely positive. Right? So let's say the object is now moving down. Right? So on the way from here to here, the displacement is still considered as positive because it only depends on where the object is at, which is actually in this case above the reference point. So it's still positive displacement. So therefore, if it goes down past the equilibrium, so on the way from here to here, the object is below the reference point, so therefore the displacement will be negative. And if let's say the object moves back up from here to here, all right, so but because the object is still located below the reference point, so the displacement is still negative. Now, what about velocity? In direction of velocity depends only on direction of motion. So what does it mean by direction of motion? So if you're taking upwards as positive, every time it moves up is positive, every time it moves down will be negative. So moving up here, velocity is positive. All right, moving down, velocity is negative. Moving down, velocity is negative. All right, so let me just write it down. And finally here it is moving up, so the velocity is positive. Now what about acceleration? Now according to our kinematics, direction of acceleration depends only on direction of net force. So from the previous slide we have seen that if the object is above the reference point, the restoring force of the spring will be less than the weight, but if the object is below the reference point, the restoring force is actually bigger than the weight. So what does it mean? So every time the object is moving from here to here, the object is actually above the reference point. So above the reference point means that the net force is actually pointing downwards because the weight will be more than the restoring force of the spring. So in other words, when the object is here, moving from here to here, the object is above the reference point, so the weight is bigger than restoring force, so net force is downwards. So net force downwards, acceleration is downwards, so therefore acceleration is negative. The same thing goes for this part. Even though it's going down, it doesn't matter. The object is still above the reference point, so the weight is still bigger than the restoring force of the spring. So the net force is downwards, so net force downwards, acceleration downwards, so your acceleration is negative. And when the object is past the equilibrium as it's moving down, the what do you call it? The weight will be actually smaller than the restoring force of the spring because extension is bigger. So therefore, the net force is up, so acceleration is up, so the acceleration is positive. Same thing goes to the other side here. When it's going up, the object is still below the reference point, so the weight is still less than the restoring force, so the restoring force is bigger, so net force is upwards, so acceleration is upwards, so it is positive. All right, so this is how you would interpret the displacement, velocity, and acceleration at different positions. Now, we also need to know when is or at which point do you have maximum velocity. So, do you realize in all simple harmonic motion, for example, in a simple pendulum that you've probably done in your lab, as you swing from one point to another, do you realize it's moving the fastest in the middle? Right, so in the middle, you're always having the maximum velocity. So Vmax will be in the middle. But as it reaches the highest point here or here, it will stop. So therefore, when it reaches the highest point here and here, the velocity will be 0. All right. What about acceleration? Now, acceleration depends only on net force. So therefore, in the middle, which is equilibrium position, there will be no net force. So therefore, the acceleration here is 0. But the further away it is from the equilibrium, the bigger your net force. So it makes sense that the highest point you have maximum acceleration, and the lowest point you also have maximum acceleration. Now, some students have this confusion. They said, how can you have maximum velocity when there's no acceleration, and how can you have zero velocity when you have maximum acceleration? Now, this is due to a misconception that the acceleration depends on the value of velocity. Now, acceleration does not necessarily depend on value of velocity, because acceleration is defined as rate of change of velocity. So what happens is acceleration actually depends on change of velocity and not just the value of velocity. Meaning to say, why is it here is maximum velocity but no acceleration? Because at this point, the velocity doesn't increase or decrease for a short while, so there's no change in velocity, so there's no acceleration. Example, now when it stops here for a while, why do I say the maximum acceleration? Is because your net force is the highest, but also what it means is from here onwards, at the start its velocity is going to increase at the highest rate. All right, so the velocity increase very quickly here. But as you go down, the acceleration will drop to 0. So meaning to say, from here to here, the velocity will still increase, but at a slower rate. Now, until it reaches here, then the velocity will not increase anymore, so therefore acceleration is 0. Then it passes the middle, then it starts to slow down, so there's a change in velocity, so there's an acceleration, and you reach here, you have maximum acceleration, because when you're about to stop, you experience the biggest change in velocity. Same thing, when you start to move back again, you also have the biggest change in velocity. So therefore, you have the highest acceleration.